Binaries. I've been working on understanding the dynamics of formation. My special interest is in understanding how terrestrial planets and possibly habitable planets can form them and whether we can detect them. I've been working on that for quite a while, and it turned out that there's a long and very nice history behind it. So I thought, instead of actually giving a formal talk, why don't I go ahead and talk about the history of the planets in binaries and the current status of research, both theoretical and observational, and then present the actual problems and how much we know about it and what has been done, things of that sort. And then basically asking questions, and we'll see where we are going with this. If you look into yes, I have to. Okay, so that's the big. There we go. So if you look into literature, you'll see that planets in binaries and understanding their dynamics goes back to at least 40 years ago, when Oppenheimer started thinking about what happens if you want to form actual planets in binaries. And then later on, people like Widmeyer came up with the idea of habitability of planets in binaries. And during the decade of 80s and 90s, a lot of papers on dynamics of these objects. But it was, they were all basically on hypothetical systems. And it was slides like this that observers, actually theorists, they constantly were using to say that you're not going to be able to get planets in binaries. Either you will have a fast rotating cloud that is going to give you a binary system, or you're going to have a slow rotating cloud that is going to give you planets. This is a slide from the book Moons and Planets by Bill Hartman, and I made this slide in 1999. That was the state of our understanding of planets 10 years ago, but things have changed drastically, as I will explain to you. There were also simulations like this by Artemovich and Lubo. They were saying that if you have disks of circumstellar disks around the components of binaries, as long as they don't interact with one another, they go on circular orbit, they're safe. But once you have eccentric binaries, then disks may truncate each other something from 50 to 90%. And that causes material that is going to form planets go away, and you are not going to have planets in binaries. Well, it turned out that observers knew better. So in early 80s, Gordon Walker and his group, they developed this technique and an instrument, the iodine cell, that they were trying to use to find planets around other stars. And they made this instrument, and they were using it, they were testing it by looking at the radial velocity of about a dozen of stars. And among them was Gamma Cephei. Is a primary of a binary system. And in 1998, they published a paper. They said that there may be, when they look at about 6-7 years of radial velocity of Gamma Cephei, they said that there may be a planet with a period of 2.7 years and about mass of Jupiter, or maybe twice as mass of Jupiter, around this primary star. Well, the idea that planets can be in binaries was so strong at that time that even they themselves didn't believe what they were saying. And later on, they retracted the discovery. So in 1992, Gamma Cephei was classified as K03 star, and then based on that, they were saying that if you look at the star, you will see the chromospheric activities that has the period of exactly 2.5 years. So what you see may not be an actual signature of the planet, may be the chromospheric activities. So as a result of that, in 1992, Walker et al. Published a paper, and they said that most likely what they found was not a planet, and it was actually the activity of the star. They retracted their discovery. It took another 10, 11 years to observe that star, and finally Hatzius et al. In 2003 published a paper. They went ahead and they put radial velocity search from 4 different telescopes, and starting from pre-1985 all the way to 2002, they put that together, and they finally came up with the conclusion: no, the planet is real, and there is actually a planet with a mass of 1.7 Jupiter mass at around 19 AU with eccentricity of 0.12 around the primary star. And that was the beginning of the whole field of planets in binaries, and once that was announced, a lot of people started looking into how this planet was formed, whether this is typical or not, and what would be the condition for a binary star to have giant and terrestrial planets. This is a cartoon of how Gamma Cephei is. The planet is very close to the primary star. Primary star is a K4 subgiant. The secondary is is an M dwarf, is a 0.44 solar mass. This separation is about 19 AU with eccentricity of 0.36. The planet is at 2.1 AU and with eccentricity of 0.1. Yeah.
The D component by direct imaging, right? Recently.
Right.
Actually, the orbital solution was even more severe, the eccentricity of 0.6.
Okay,
as far as I remember, making the problem, of course,
even
harder.
Yeah, even harder. That is true.
I just wanted to point out that the second component, its properties are known pretty well now.
Right.
That's right. Everything possible, and it's really reliable.
Right.
0.4 is correct, actually. I mean,
Right.
The that they found.
So some people said that this configuration is actually a secondary configuration. The planet was formed around the primary when the binary was wider, and because of interaction with passing star, the binary collapsed to what it is. This is an idea that was put forward by Eric Fall in 2003, 2004. But many people, including myself, try to understand whether we can actually form planets, either giant or terrestrial planets, and what we can learn from systems like this. Well, observers, right after that discovery, observers went back and looked at different stars, and they found a lot of evidence of planet-forming regions in and around binaries. I'm going to just show you a few of them. This is GG tau with a separation of 35 AU with a circumbinary disk. This is another one, 14, 15, 69. The separation here is 950 AU. There is a disk around one of the components. This is UZ tau. This separation is 500 AU. And there is circumstellar disk that can form planet with a width of 50 AU. This is the favorite of theorists. This is L15551. The separation here is 40 AU. Each disk is about 10 AU in radius, and each disk has about 6% of solar mass. So it's massive enough to form planets. This is a recent discovery made right next door to my office. 2 disks with separation about 200 AU and with masses comparable to minimum solar mass nebula. This is another observation that Trilling and all did with Spitzer telescope. What they're showing here is the percentage of binaries that they have disk around one component or circumbinary. The observation was through 7 micron axis or 24 micron axis. This is the axis because of the dust. The way that it works is that, for instance, look at the 7D. 7D says that for binaries smaller than the 1 AU separation or maybe 5 AU separation, about 47% they have disks around one component. When you go for around the entire binary. When they go for binaries larger than 100 AU, then there is something about 45, 43%. There is a lack of disk in the regions where the separation is moderate, something between, say, 10 to about 50 or 100. And they weren't able to find very many disks around those components. So this is the status of the research. At the end of my talk, I'll tell you about the actual dedicated searches that are looking for planets in binaries. But with this, let's go ahead and see what is the situation with the current status of planets in extrasolar planets in binaries. This is the situation. There's about 20% of them are in binary systems. This is almost complete. There, since 2006 that I made this table, a few more have been found. One critical point about this table is that, except for a couple or 3 cases here, majority of these binaries, they are white. The separation is between, say, 250 and 12,000 AU. In 2003, James Norwood, student of mine, and I showed that for a binary with separations larger than about 100 AU, you can basically ignore the effect of the binary companion on planet formation around the other star. So something like 5,000 AU, 5,600 AU, basically you can ignore those cases and as binary cases and treat them as two individual single stars. But there are three cases that stand out. Gamma Cephei, GJ86, and HD41004, they have separations of about 20 AU, and they have Jupiter mass planet around one of the components. And now the question is how these were formed. So, like I said, many are interested in cases like this because of two reasons. One, we would like to see how this giant planet forms. Second, once these systems do have giant planets, so the next question would be how can we learn about binary system with giant planets about terrestrial planets formation? And how can we compare that with our solar system? In our solar system, terrestrial planets were formed when giant planets were already there, and giant planet affected terrestrial planet formation profoundly. So the question is, can we compare this? What we learn by applying that idea to this, and can we compare terrestrial planet formation in these systems with our solar system? So the main question is how these planets were formed, how is planet formation in binaries, in basically moderate closed binaries. So we are talking about binaries that are with separations between, say, 10 and 40 AU. And whether that formation will go the same way as around single stars. And like I said, this is what, if you ask those who work in this field, this is what they put up. And they say, well, there are systems like that. And the separation is long enough for each disk to do their own things. The disks are massive enough to form giant planets. They're also wide enough to have enough material to form planets. So the answer to that question apparently is yes, we can take planet formation theories in, around single stars and apply it to binaries. But the story is not that easy. So let's start with this is what we know from planet formation. We start from dust coagulation and then we go all the way to giant and terrestrial planets. The question is how these things will behave or will change as you introduce a stellar companion to the system. Well, it turns out that the work is very, very complicated, and the best way to understand how this thing works is actually to start from the bottom, start from here, simply because when you go to the latest stage of terrestrial planet formation, you will have all these protoplanetary objects, moon to Mars sized objects, that they interact with one another and they grow to terrestrial sized bodies. And that stage, you can actually analyze it just by n-body integrations. But the previous stages that eventually lead to that stage or become more and more and more complicated. So the way that I'm going to explain it is start from this one and work my way backward and explain why we need the previous stage and what is the complication with it. Jack Lissar did a good job explaining some of the results they got for terrestrial planet formations in Alpha Centauri system. This is one of their simulations, and as he explained, they put several moon to Mars size objects and they let them interact with one another, and within a couple of 100 million years they were able to show that simulations result in terrestrial planets. Some of these terrestrial planets are stable, some not, but in general it looks like the idea works. Because I was interested in binaries that already have giant planets in them, I went back and looked at this system and tried to understand whether this system can have terrestrial planets and whether we can form terrestrial planets in systems of this sort. So what I did was that I put a lot of Earth-like planets in this region and studied the stability of that. Oops. Okay. And studied their stability. This is what I'm showing here is Gamma Cephei, the Jupiter-like planet is here, the binary companion is sitting all the way back there, and the primary star is here. Each one of these lines correspond to lifetime of an actual Earth-like planet, Earth-sized planet at different positions. The habitable zone is back there. And this study indicated that if you get close to the primary star, as we expect, if you get close to the primary star and you're far from the influence of the giant planet, then you will have some stable region. So when we saw that, Sean Raymond and I thought of the following scenario. We thought that, okay, why don't we go ahead and make a model that resembles solar system, but then introduce a binary companion and see how that would affect the whole terrestrial planet formation. So we made something like this. We took Sun, and this is the habitable zone. We put Jupiter at 5.2 AU with no eccentricity, because we wanted to see how that would actually affect when companion would get close to it. Then we put the stellar companion with different masses at different distances with different eccentricities. And then we put a lot of protoplanets around primary and basically outside the influence zone of Jupiter. And then we assigned some water content to it. We said the ones that are closer than 2 AU, dry, between 2 and 2.5, 1% water, and larger than 2.5, 5% water. And we let the protoplanets interact with one another for different mass and orbital characteristics of this object, and keeping this one right at 5.2 with no eccentricity. This is one of the slides of some of the results that we got. A solar system is here at the bottom. Sun is sitting here, and binary companion is somewhere over there. This is the Jupiter-like planet of the system, or Jupiter in our case. And so simulations are for different eccentricity and semi-major axis of the binary. And as you see, there are cases that you can form terrestrial-sized planet with some water in the habitable zone of Sun. Basically, it's telling you that depending on the orbital parameters of the binary companion, you may or may not be able to form Earth-like planets. Now, what is shown here is very interesting. As the semi-major axis increases and the eccentricity increases, the amount of water that is delivered to terrestrial planet decreases. Like, for instance, look at cases like this. Because of the close approach of the binary companion to the giant planet, and then from giant planet to the disk of protoplanets, a lot of that material gets ejected from system. Not much goes to the formation of terrestrial planets, and not much water is delivered to the system. But the ones that have low eccentricity, they manage to form planets with some water in it. So this immediately told us that if we want to understand what's going on with terrestrial planet formation, we got to go one step back and learn about giant planet formation and the orbital giant planet formation. Yeah.
Just out of curiosity, what do you get in this model if you don't put the binary in the companion? Do you reproduce something similar to the solar
It becomes something similar to Earth, yes. It's basically the same simulation that Sean Raymond is doing. It becomes basically the same thing. Right? So this told us that in order to understand this part better, we have to understand this part, formation of giant planets, better. So the question is how this giant planets form. Well, there are several groups that are working on it. And the two scenarios, disk instability and core accretion, they tell us different things. For one, core accretion, if you want to do core accretion, you got to go back to learn more about protoplanet formation and the transition from planetesimals to protoplanet. I'll explain that. It has its own complications. But Lucio Meyer has been able to show that if you do disk instability, you may be able to form giant planets around the components of a binary. However, the mechanism works for binaries beyond 100 AU. The reason is that Andy Nelson, also one of the people who does disk instability, has shown that for binaries around 50 AU, neither core accretion nor disk instability will work and will produce giant planets. So they were able to show that once you increase the separation of binary to 100 AU or larger, you may be able to get giant planets forming around the components of each component of the binary, but that is as much as we know at this stage. For the core accretion, well, it becomes even more complicated. To understand how the core accretion does, you got to basically understand how protoplanet forms, and that is what relates to the whole theme of this workshop, that the disks and dynamics of disk in protoplanets and all that. I haven't done much simulations in this category, but I'm going to review what people have done and then open the floor for discussion. Well, remember the simulations showed you for Ardmovich and Lubo in 1994. They showed that much of the material will go away and not much is left. This is simulations 2004 by Tibarel. What they show here is they take a test particle. This thing is test particle. And they put it in a binary. and they see what happens to the test particle's orbit as the binary interact with it. This is a better, this is basically a more complete version of what I just showed. They have test particles, and they notice that the eccentricity of the test particles increases. These are just different snapshots of the system. This eccentricity increases. The dashed line shows the average relative velocity of two objects that may hit each other. So when they got this, they were like, okay, it looks like if we have planetesimals, kilometer-sized objects, and we put them in a region between binaries, because of increase of eccentricity, the relative velocity of these objects may increase as well, and then when they hit each other, they may shatter one another. Well, it turned out that it is not exactly like that. When they included gas drag to the system, then things changed. Basically, they noticed that just by considering test particles, the simulation is not going to work. You have to actually consider actual object and let that interact with the gas. Then they noticed that in that case, the gas drag will align the orbit of planetesimals, and that will reduce the relative velocity and let the objects hit each other in a more efficient way. And this is basically what it's showing here, that for two planetesimals, two planetesimals, let them interact with one another, the orbit aligns after about 10,000 years, and that's the way that the eccentricity evolves. They also noticed that this alignment is size dependent, and that actually dictates how planetesimals interact with one another and how this collision and growth will evolve. This is similar simulations for a 5 kilometer and 1 kilometer object, and as you see, the 1 kilometer object eccentricity increases, but not as much as the 5 kilometer, and the 5 kilometer reaches the alignment much longer than 1 kilometer objects. From that, this is the map that they produce for possibility of collisional growth of planetesimals. In the region that basically you're away from the perturbation of the binary companion, as you see here is semi-major axis, this is eccentricity. When planetesimals are safe from the perturbation of binary companion, they may be able to interact with the gas and grow by colliding each other. As the eccentricity increases, the more close approach of the binary, then that picture goes away, and the accretion gets perturbed by perturbation from the binary. The alignment is not going to be as efficient to keep the relative velocities low, and as we proceed, we see that the accretion becomes less efficient, less and less, and finally it results into erosion. And they use that to say that for Alpha Centauri, this is basically the situation. Now the graph has flipped. Here you have the same major axis, here you have eccentricity. For high eccentricities, basically no accretion is going to happen for the terrestrial planets. For low eccentricities and far away, you will get accretion. This is something that we would expect to see. This is another simulation of the same type, but then allowing the interaction, the collision between two objects. So basically they're showing collisions between 1 and 5 kilometers objects, 1 and 1, and 5 and 5 kilometers. And again, it shows that, for instance, look at 1 and 1. The collision is, the relative velocity is lower, collision is more efficient to form bigger object, whereas for cases like 5 and 5, the relative velocity, the velocity at the time of the collision, time of impact, is going to be much higher, and that may result into erosion and fragmentation. This all resulted into the conclusion that in systems like Alpha Centauri, the collision and the growth of planetesimals, two protoplanets, is very much size dependent, and also it depends on the orbital parameters of the binary. This is the collision between two different sizes of objects. As you see, the green one is the one that allows for collision and growth, and the others basically prohibit growth, and collision will result into shattering. As they show here is that, what they show here is that if you have objects of same size, especially smaller objects, you will have better accretion than objects with different sizes hitting one another. The same thing this time for Alpha Centauri B and A in the habitable zone, basically showing that the habitable zone for A between 0.5 to and 0.9 AU basically it's hard to form something there, and the same for A, it's going to be hard to form something there as well because the region is not friendly to collision accretion. What they didn't consider was the fact that when you form these protoplanets, then there will be interaction from the protoplanets to the gas and vice versa. And protoplanet will affect the eccentricity of the disk, and the disk will fit back to protoplanet and affect its eccentricity as well. So these are simulations by Clay and Nelson. Here is the original gas in the disk, and each color shows different times, and it shows how the eccentricity of the disk changes as the disk interacts with the forming protoplanets in the disk. They only considered one protoplanet in the disk and interaction with that. Now look at this one. This is for a test particle, and these are all for protoplanets. It clearly shows that when you include the protoplanet in the disk, if you don't consider the interaction, then you may actually lose your protoplanet to the star, or the protoplanet may have high eccentricities, and when it hits another one, they may get shattered. So this was another complication. In the previous simulations that I showed, they didn't consider this into effect, but then once you take this effect into account, then the growth becomes even more complicated. This is another simulations by Clay and Nelson, basically show that depending on where the object starts, these are 3 runs of same type of object, same type of protoplanet at different places in the disk, with and without accretion, and depending where they start, they may result into collisions, may result into fragmentation, or may result into accretion, depending on where the object starts and how its eccentricity changes. Another important factor that were not taken into account in those simulations was inclination of the orbit. Jiling is going to talk about that more in detail, but I just want to show this one slide to say that the inclination basically results into size sorting. And if inclination is small, the separation of the sizes may result into accretion, but if inclination is higher, especially with high eccentricity, then accretion may not happen. What Marzari et al. Are showing here is that for no eccentricity, this region is accretion friendly. That's the region that accretion is no good. And you see that you go farther away from the primary, you're in a better shape to accrete material planetesimals. And the accretion zone becomes smaller and smaller as the eccentricity increases, especially for the different inclinations. For higher inclinations and high eccentricities, you basically don't get anything in the vicinity of the star. And they said that if you have high eccentricity binaries with high inclinations, the accretion-friendly zone goes beyond 70 AU. This is another simulation. I just want to mention this. This simulation doesn't take into account gas. What it does is that Tsukamoto and Makino, what they did was that they took a huge swarm of planetesimals and they put it in a very tight region, and they let them interact with one another and also with the perturber. And they say that the same way that tidal interaction in our solar system, tidal interaction because of Jupiter in our solar system has circularized the orbits of planetesimals, is possible that the tidal interaction because of the binary companion circularizes the orbit of the planetesimals around primary star as well, and get them aligned and reduce their relative velocity. This is something that has been worked out as well. Now back to the questions. I'm just going to finish in a minute. Back to the questions. Do we know dust coagulation? We really don't know. You know, what's going to happen for dust when there is a binary companion over there? Something to work on. Planetesimal formation. All the problems that we have with formation of planetesimals from dust growing all the way to kilometer size exist for binaries as well. Do we know what happens when there is a binary companion? No. Is stream instability still a viable mechanism? Maybe. Is what's going to happen to collision growth of centimeter size objects? We don't know. The meter size barrier still exists. These are all open questions. Protoplanet formation growing from kilometer size to moon to Mars size objects. It looks like we are getting a handle on that, but still work to do. It looks like if we have moderate to large eccentricity for the separation of the binary, moderate to large semi-major axis for the separation of binary, and low eccentricity and inclination, we should be able to do that, but still we have to take into account a lot of interaction between protoplanets as they are growing with the gas and vice versa. Giant planet formation, disk instability, maybe. Core accretion, we still have to work on this part of it to get to that, so that's still an open question. Terrestrial planet formation, it looks like the very late stage of terrestrial planet formation, we can do that. We can take a binary and try to understand whether terrestrial planets can form in there or not. So these are open questions as far as planets in binaries goes, and this is basically the current state of theoretical research. As far as observation, these are dedicated, well, some of them are dedicated searches for planets in binaries, and some do planets in binaries. But before I explain that, the Carnegie, California Carnegie search has deliberately excluded all binaries. Any binaries closer than several hundred AU, they just didn't consider that because they didn't want to contaminate the data. However, there are searches, and there have been searches like SARCH that were dedicated to look for planets in binaries between 50 and 500 AU. This search started in 2003, and unfortunately they haven't been able to find anything, but well, maybe we should wait longer. And then there is Corelli, Elodie, and Cravel by Egenberger and Udry. They haven't been able to find planets in binaries with separations smaller than 20 AU. However, they have been successful in finding binaries, planets in binaries with 100 AU or maybe larger. Their focus is primarily on G and K stars. SIM, hopefully it'll go up, and if it does, then there will be a program in it to look for planets in binaries, but again, depends on where it's launched. So this is all I wanted to say. I'm gonna stop here and let Jilin continue with the role of inclination in accretion in binaries, and then if there's any question or discussion, I'll be here. Yeah. Sure.
Question?
Yeah, if you have questions, yeah, please.
So maybe one very short comment. It does not solve any problem, it just strengthens your points with the observation. So just to mention, what most of the people do, they search for planets in binary or multiple systems.
Right.
There is also another approach, and I mean, I'm just working door to door with the people who use another approach. What they do in Jena and Tautenburg, actually, you mentioned Archiaxis many times. But in Jena especially, they take no exoplanet host stars, okay, and they search for binarity or multiplicity. So it's not exactly the same. So we know there is a planet around that star, for example, RV planets, and we look if there might be some unknown companions.
Correct.
And they do that by direct imaging, and interestingly, they are quite successful. So over the last 5 years, they published heaps of papers with the new discoveries, sometimes confirming what was known spectroscopically, for example, gamma sep is one example. But the point is that it does lead to the same number as you quoted. So they find, actually you mentioned 20%, they find 17% known exoplanet for stars at least.
Right.
Have at least one component, and actually what makes the problem even more severe sometimes, there are even some triple systems.
Right.
So they found some.
That's correct.
Right.
Well, I personally am hoping that when Kepler releases data, then we'll be able to actually dig into that and get, If you notice, I didn't say anything about transits in binaries or transit timing, things like that. So I have my hopes that Kepler may actually increase that percentage from 17 or 20 to much higher. But at the moment, you're right. Yeah, there seem to be radio velocity searchers seem to not be doing a good job in finding planets in binaries, and the percentage is going lower and lower.
One quick question.
Sure.
Do you consider AC 20, 22, 06 circumbinary planets?
Say again?
Do you consider this, there is this system where you have solar type star and you have like a 17 Jupiter mass planet?
Or do I consider those
Yeah.
as,
As
do I
a-
consider those as
and there is
binaries
a
or?
planet as well, a low mass
This-
planet
no.
that is circumbinary.
No, no,
You
the,
don't- you
no,
don't
no.
think- okay.
The system that I put here, they don't have any brown dwarfs in it. They're actually two well separated, well recognized stars.
Okay, so shall we begin?
Yeah, please.
Yeah, thank you, Nader, for your exciting introduction. So I'm Jin Zhou from Nanjing University, China. So I will keep going to introduce a little bit what we have done in the specific problem, namely the planetesimal accretion in the binary systems. So my collaborators from Jwei Xie, my PhD student in Nanjing University, also Jian Ge from University of Florida, take part in the jobs. So as mentioned by Nader, so one of the problems in the planetesimal accretion in binary is that due to the perturbation of a companion stars, the eccentricity of the planetesimals are excited. So that when during their accretion, so their relative velocity is huge. So that means the accretion rate is small because without gravitational focusing, then the accretion rate should be low. So what we do is we try to find some methods, mechanisms to reduce the relative velocity for during the accretion. So first of all, let's have a look about what happens a planetesimal in the binary system. So without any gas first. So for example, if a planetesimal is put in the binary system, then it's essentially should be pumped by the second star, and also the perihelion, the longitude perihelion, periastral could also be aligned with the binary companion. So basically, a planetesimal will circularize librate here or circularize like here around the equilibrium solutions like here. So this is a case that without any gas. But when you put gas disk in, then basically they will slightly, gradually drive in, down to the equilibrium solution. Also, the point, the perihelion difference is not necessarily zero, but with slightly difference with zero. So that's what happens when the gas disk is included. So those two plots shows the situation that you see without gas, the eccentricity, different locations, this is for semi-major axis, different locations of planetesimals, they will get excited by the eccentricity excited, and also their longitude of the periastral will be liberated at different locations. But when you add gas disk, though, then the gas disk will be, the planetesimal will be eccentricity of that planetesimal will be totally excited, and totally they will gradually drop into the equilibrium solution. So all the planetesimals have one eccentricity, also have one perihelion longitude. So this we call this kind of orbital alignment. This effect. The effect of orbital alignment is good for the planetesimal accretion because you see due to this same orbital phase, the relative velocity will be reduced, right, for same size of a planetesimal. So this is good. But another point is that if you have different size of planetesimals, then we will show that the accretion rate, the equilibrium of different size of a planetesimal are different. So that's may cause a problem. So you see, so for same size of planetesimals, the orbit alignment configuration in makes them have a slow, have a smaller relativity velocity like here, because both of all the planetesimals have the same direction in this one. Unlike this is a line orbit alignment situation. But as we mentioned that for different size of planetesimal, the equilibrium solution or the final state, they are under gas disk are quite different, slightly different. So that makes what? Makes if they are different size of planetesimal, they have different different orbital configurations. So if the collisions are mainly occurred among different size planetesimal, then their relative speed is still very high. So this is a problem. So how can we reduce the relative velocity among different size of planetesimals? So to achieve this goals, we have to propose two mechanics. The first one, mechanic is that if a gas disk depletes very fast, this could happen like 100,000 years in the binary system. It's possible because due to the binary company try to hit the disk, so the disk may be photoevaporate very quickly. So in a fast dissipated gas disk, so the after the gas dissipate a lot, but still they have some gas, then the equilibrium state configuration of different size planetesimal almost come to the same one. So then finally they got the same orbital configuration. So this is a simulation, like the final state simulation. You see, we have different size of planetesimals. We use different colors to show here that this is the final state. Like every planetesimal, they have almost the same eccentricity at one location, and different size planetesimal, they have longitude of perihelion almost near zero. So at the end, but how to see that? In the beginning, we put all the eccentricity at zero. In here, and you can see that soon with the evolution, they will different size of planetesimal, they will have different configuration. But when the gas depletes finally, and then all the different size planetesimal, they have reached the same configuration. That means their accretion, the relative speed will be reduced. So let's show the animation. I hope it works. Okay, see. So in the beginning, the different size of particle, they have different orbit configuration. But finally, you see the omega minus omega binary is slightly equal to zero. So all the planetesimals, they have same configuration. So that's the end of okay, this is one mechanics, and also we use this mechanics to explain the gamma several system at 2 AUs. You see, if the gas disk is constantly do not dissipate at a time, so you see the different the collisions among different size. This is a different size of planetesimal. The collision, the relative speed in constant velocity is quite high, so 600 meters per second. So the collision will lead erosion. They are not accretion friendly. So, but if you see the gas depletion, which occurs like 10 to 5 years. So after like 10 to 4 times 10 to 5 years, most the accretion, let's see, in constant velocity is reduced because most planetesimals, even with different size, they have the same configuration. So in constant velocity is reduced greatly. This is second mechanic, and for the second mechanic, we propose that if the disk is not a planar disk but have a slightly small inclination, maybe only 1 degree is needed, then you see you have, if it's coplanar, then all the planetesimal have here, so their collision have their high velocity, relative velocity. But if they have small inclination, that remember that different size of planetesimal, their in equilibrium configuration and the gas are slightly different, even in the also with a different final inclination. So they will stratify in the Z direction. So that you see like here, like 10 to 4 years. So they were sorting by the size, different size. So that means collision can only occur with same size. That means also that the collision relative speed are quite greatly reduced by this kind of mechanics. So only 1 degree is enough. We don't need too much inclination. But of course, because now this is a 3D problem, so the collision time could be elongated. But you see, all the collisions is collision friendly. So you see that in the planet problem, you see the relative velocity is like around average like several hundred meters per second. But in the inclined system, it can like between 10 to below 100 meters per second. This is the relative speed, and also this is a ratio that the collisions is friendly or not. The red one is not erosion zoom, so collision is not possible. But for a planet, you see most of the region, most of see less than only less than 10% is collision friendly. But when you have a disk with a slightly inclined disk, then see most of the regions seems that they are collision friendly. So by this, you see, we think that in the system, in the Alpha Centauri system, it's possible from terrestrial-like planets, like around the habitable zones. See, most of the regions are collision friendly. So here comes my conclusions that so a fast decay disk is helpful to decrease relative velocity of planetesimals, and in a slightly inclined disk, planetesimals are stratified in the vertical direction for different sizes. So this will lead to the low relative speed, and planetesimal accretion at 1 to 2 AU around the Alpha Centauri system is possible if a inclination is like you give a small inclination, and the accretion time is roughly estimated by some formulas. By this, I think I need to finish it, and I'd like to have some questions. Thank you very much. Yes?
So are you allowing the disk to have any dynamics? I mean, shouldn't the disk also be eccentric?
Oh, yeah, but we are mainly planetesimal disk. I mean,
The gas disk?
In our simulation, our gas is sometimes decreases, some constant, but we do not consider the disk as the shape of a disk. No dynamics.
Right, but it's natural for the gas disk also to
Yes, that's true, but I think that's the second, the second effect. So we need to consider more, because you see, basically the whole thing, the first order is just like how to say, a flat disk or just like a slightly inclined disk. But then you have slightly inclined. That is a second effect, maybe.
It might change the relative. Might change the relative behavior of the different size.
Yes,
we did some simulations of gas disk dynamics with these planetisms embedded. And if you, for binaries that you usually consider 20 AU separation,
yes,
you get a very eccentric gas disk actually. There's probably this 3-to-1 resonance that bumps up the free eccentricity of the disk, and that
I see.
actually that doesn't help you at all. Because the gas disk will then, I mean, there will be this differential orbital phasing, but it will be much stronger because they're phasing to an eccentric gas disk, which is gases has a free eccentricity which can exceed the eccentricity of the binary.
Yes, could be, yeah. So,
But even if the disk doesn't develop a free eccentricity,
Well, that's if it's. I mean, that's what we were trying to look for.
yeah, but
If the gas disk would tend to the forced eccentricity due to the binary, then there would be no damage towards this. But it doesn't seem to happen.
It might depend on what your initial. How do you start this
Well, you can, it's, so we started with basically unperturbed gas disk.
That's, what is an unperturbed gas? Circular?
Yeah, it's,
Oh.
well, you can start it eccentric, and it will. All you need is for the disk to have. As soon as you have some material in this 3-to-1 resonance, then it will shoot up.
Yes.
What's the mechanism for stratification?
Stratification, because see the different size of planetesimals, they have different how to say equilibrium solution, equilibrium point under gas.
You start with that, or you get.
No, you interval automatically. Because you see under the under the gas drag, so different size of particles, they will have different initial finally have a different final eccentricity, also have a different final inclination. That they are equivalent in that state. We didn't need to set it. You can see that.
You don't need
that
the
is, yeah.
resistance, or do you?
No, of course it consistent, because you see that it's it automatically evolves. You see like here. So and initially everything have different size in essentially inclination, and see that the 1,000 years they aligned it, and 3,000 and 10 to 4 years they have a different inclination, so they are stratified already.
So did you have a question? Did you have a question? Yeah, yeah.
Oh, I guess I can have one, yeah. Well, I guess what I was wrong in a similar note to the eccentricity, I was wondering if, since quite small inclinations are quite important here, you imagine in general the gas disk would not necessarily be completely aligned with the plane of the binary, and so it might be similar to the eccentricity. There might be a dynamical question about whether the
Yes.
disk is actually warped and processing. There
Yes.
might be a question about whether the damping is shorter than the procession time or not.
Yes.
Whether that would affect.
Yeah, that's quite very interesting. Thank you for. But I think we need to study that.
This wants to be.
The gas disk waves in it with shape.
It's all possible. It's possible.
Yes, Gersh.
Good.
5 more minutes for our time. So.
Plane which you measure the inclination should be possible.
But I guess I'm thinking that the disk actually has a plane that varies with the distance. Actually, the inclination is not constant with radius. So.
Yeah, but that warping is being caused by the secondary, right? That just creates a new velocity plane. The particles, travel lines.
Right, with the gas drag.
Yeah.
Due to the gas drag. So,
Yeah.
so the question will be whether that timescale for alignment
Well, it won't start off any different.
is short or long. Okay.
Well, why would you ever assume they're not aligned? Gas is found in some ability to align. Why has the particles not done it? They're coming from the gas initially, right? They're basically condensates from the disk. So why don't they just do the same thing? So it's a question of initial conditions.
So if the gas disk is warped, and say then it's processing at some rate, which is not local, but is just set globally by the gas effect as well as by the perturbation, there will be some,
Well,
there will be some differential effect between the solids and the gas. Okay.
Yeah, I mean, both cases of eccentricity and inclination, the dynamics of the disk questions or discussions?
I'm also wondering of the chances for a planet formed in a binary system to survive after the gas is dissipated. I mean, for one planet it's probably no problem, but if you have a system, the eccentricities will be bumped up by the binaries, so this may lead to close encounters, disruptions of the system.
Right, so it
or-
pretty much depends. Right, it pretty much depends on the separation and the eccentricity of the binary.
Yes.
Smaller separation and larger eccentricity will give you very narrow bands of stabilities.
Mm.
And so unless you form planets there or your planet falls there, you're right. Many of these planets will go away. Like in our simulations for terrestrial planets, we ran our simulations for about 100 to 200 million years, and we were able to show that we will get some of these planets, some terrestrial planets. But then if you carry on for about 500 million years or a couple of billion years, only a few of them survive. So basically, you're right that there will be just narrow bands of stability as you can put this stuff in there, especially when they are formed and they interact with one another.
And do you already see a trend for that in the observations, for the closer binaries? Is there a tendency for small eccentricity to have more planets?
Not really. It's very scattered. It sort of varies from one system to another. Maybe we should do more analysis of that. But with what we have done so far, we don't see any trend.
Just a short question, Nader. In your list of consecutive phases, you mentioned also possible influence for the very first step, dust coagulation, something like this. Are there any problems actually?
I
Do you have one problem less? Or
I
your
don't anticipate.
dust
I think that
coagulation-
I think that part will go similar to around single stars.
Should be the
and
same, right?
Yeah, it should be the same.
One problem.
Right, I agree with you. But I just put it there to just have a complete picture of where we start and where we end up. But I agree. I don't anticipate any problem with binarity there.
Which will have those sizes we are about to start.
So what if you have a very wide binary, let's say a couple of hundred to 1,000 AU, but it is very eccentric, so that its Q is, let's say, 20 or 30 or something, maybe 40, then how long does it take for, let's say then it rushes through pericenter, it will, and there's a disk, so it will then,
approach for Q, right?
yeah, the Q, the pericenter distance is about 40, 50 or whatever. Let's say it's a couple of times or close to the edge of the disk. And as it rushes through pericenter, it will excite all sorts of modes in the disk. I don't know how long it takes for these modes to damp down in the disk. Maybe 1,000 years, anybody? Does anybody know how long it takes for the eccentricity in the disk to damp down? Assuming there are no perturbations? If this damping is short compared to the orbital period of the binary, then I wonder, does that favor planetesimal formation and planet formation, or does it make it more difficult? So you get a periodic, the disk get a periodic kick, so to speak, and it stirs things up and then it settles down again. Any ideas?
Is it a gas disk? The gas disk, the flyby simulations are maybe relevant in the light rays, but they phase wrap fairly quickly and damp actually pretty quickly. In
Yeah,
2,000 years.
what I was going to get to is if the binary period is long compared to the dissipation of any modes excited in the disk, then perhaps it might be easier to form planets or planetesimals. But if the binary comes through on a timescale which is comparable to the dissipation timescale in the disk, then I think it will severely hinder planet formation. So if we're looking at planets in binary systems, then of course, as you said, Nader, if you have a closed binary, you can do it around the binary. And if you have a wide binary, then you can do it around each individual star. But if you have a wide binary that's very eccentric, and there's no reason to believe these systems don't exist, if it's an E-squared distribution, most of them are very eccentric, then I wonder how would that then affect planet formation in general?
Can't answer that top of my head.
All this orbital alignment happens on a secular timescale. So if the binary period is extremely long, then this part of the problem will be less important. But you still get one kick.
Yeah, but as I said, these kicks are fairly periodic. And as you said, maybe the alignment of the alignment of these things is on a secular timescale. So you're talking hundreds, tens of thousands, hundreds of thousands of years. But I was more thinking that if the disk gets very excited, then all these particles get stirred up, and then they damp down again because of gas drag and whatnot. How fast does that happen? Maybe on thousands of years? Probably shorter than the orbital binary period. It might.
There is this HD 141159A, maybe, is maybe a situation like that. It has a clearing, a lopsided disk, and a truncated outer edge, which I think is explained with the binary with a long period, and there is an object. So, and I'm just trying to remember who's worked on that. I think the time scales in the gas disks are fast, but potentially there's secular longer time scales caused by the close approach. Perhaps relevant.